Hey everybody, it's Mr. Carr again. Today we're going to be looking at 2 for day 1. We're going to be looking at the zeros of polynomial functions. Okay, so we started talking about polynomial functions and a lot of their characteristics. Today we're going to be talking about both real and complex zeros. So again, what does it mean to be a zero? A zero is whenever we cross the x-axis. Okay, so some of these some basic ones like quadratics you've done before. But then we get some other polynomials might be a little bit trickier. So let's start with x cubed plus x squared minus 10x plus 8. Now, when you have a setup like this, it's possible that you could do factor by grouping. So you look at the first two and the second, or the first set of two terms and the second set of two terms. Maybe you could factor something out of both of those that creates common factors. Unfortunately, this one will not work that way. So we're actually going to go with the graph first. We're going to graph this function so we can find one of our zeros, and then I'm going to do the rest through algebra. So here is x cubed plus x squared minus 10x plus 8. Okay, so one thing to help with this is if we use some of the synthetic division we did before. I know thanks to Desmos here, it is crossing for sure at 1, 0. If I'm just getting a rough idea just to make sure, let me just test it algebraically, make sure it does cross at 1, 0. So what I mean by that is I'm going to go ahead and do synthetic division by putting 1 here. Okay. And I'm going to do all my other steps. So we got that. And let's see what happens. So I bring the 1 down. 1 times 1 is 1. Turns into a 2 there. 1 times 2 is 2. Turns into a -8. 1 times that is a -8. And I get 0. So I have my 0 remainder. So indeed, I do have x equals 1 as one of my zeros. Okay. So that means I can do the rest of this. If I look at 1, 2, -8 here, that is representing x squared plus 2x minus 8. So the goal is set that equal to 0 and find that. So this one I could just do with factoring. So I got x and x. We got a positive and a negative. It's going to be a +4 and a -2. Okay, so I solve those out. I get x plus 4 equals 0, x minus 2 equals 0, and x equals a -4 and x equals 2. So I have 3 solutions here. I have x equals 1, x equals 2, and x equals a -4. Again, go back to the graph. We can see that there's 2, 1, -4. So we just confirm that how it works on that case. Okay, so with our cubic here, our polynomial, I should say, we can also do this word problem with this. The water level in a bucket sitting on a patio can be modeled by f of x equals x to the third plus 4x squared minus 10x plus 7, where f of x is the height of the water in millimeters and x is the time in days. On what day or days will the water reach a height of 10 milliliters? So remember, 10 is our height. Okay, so that is f of x in this case. So the way I can set this one up is I'm going to replace f of x with 10, but then have my polynomial on the other side of my equation. Okay, anytime I'm trying to solve these, the best bet to do is always make it equal to 0. That way 0 equals x to the third plus 4x squared minus 2x minus 3. This is what I'm going to graph in my graphing calculator. I want to graph this and find when does it cross the 0 there. So come back here, got my Desmos set up for this function. Now you see it crosses 3 times. Crosses this value, but there's only one value that's important, and that's at 1. I don't care about the negative values here because remember what x is representing. Even though I'm crossing 3 times, x is representing the time in days. I don't care about negatives then. So from my graph, let's do a very rough sketch here. It was up, down, up, and it's crossing here at 1, 0. Okay, so because of that being my 0 in this case, I just solved when this equals 0, and that's the only value I care about. I don't care about either of these two. So what that means is, this is x is the time in days. It reaches, let's make it a full sentence. Let's not just jump in like that. The water level reaches 10 milliliters after 1 day. Okay, so that's my full answer in context, what the x value is, which in this case is the 1, And then the 10 milliliters is what that water level height is at. Okay, so the other part of today is we're going to talk about complex conjugate pairs theorem. This is also going to lead to us modeling different polynomials based on given zeros. So polynomials with complex zeros. As a reminder, a complex zero is of the form a plus bi. Okay, so if I talk about any kind of complex number, it's a plus bi. It's an imaginary number. But whenever we have complex zeros, they always occur in conjugate pairs. This means that there'll always be an even number of complex roots. So for example, if 2 plus 3i is a complex zero, 2 minus 3i is a complex zero as well. The conjugate is referring to the plus and minus. So it's the same exact values, the same order, the 2 and the 3, but it's a positive version and a negative version. Now, since we always have these will always exist in pairs, anytime we have an odd degree polynomial, there has to be at least one real zero. Because if we have complex ones, we can't have 3 complex ones, and we can't have just 1 complex one. They have to exist as pairs. So if I have like something x to the third, and I only have 1 0, then I might have 2 complex zeros. That works out. But I can't have 3 complex zeros, and I can't have just 1 complex zero. Okay, so that's one conclusion we can always go from this. Any degree you're working with, as long as it's an odd degree, you know there's going to be at least one real zero. So how can I use this conjugate pair? We're going to look at this one right here. I want to write a polynomial function of least degree with real coefficients in standard form that has -1, +2, and 2 minus I as zeros. So remember what this means. My other zero here is going to be 2 plus I. So what I have is 4 different functions, or sorry, 4 different zeros I can model in here. So the -1 means it's going to be +1 in the factored form. The +2 is going to be a -2 here. And then the 2 minus I and 2 plus I is going to look like this. I'm going to take x minus 2 plus I, x minus 2 minus I. Okay, so that's our setup. So I want the polynomial function with real coefficients. That means I want it in standard form. So I'm going to have to distribute this all out. Personally, I like to start with the ones that has the complex there. If I do that, I'm going to distribute the x here to both of those, and then the -2 plus I to both of those. Actually, you know what? Let's do this way. Let's distribute the negative signs. We'll make that probably a little bit easier there. So we got x plus 1, x minus 2, and then x minus 2 minus I, x minus 2 plus I. Okay, so like I said, I am still going to do that. I'm going to do these two first. When I do my distribution, I kind of like doing it with a box here. So in this case, my box is going to be made up of x minus 2 minus I, x minus 2 plus I. So I'm just going to do the intersections of all these and multiply them together. So I'm going to have x squared, -2x, -xi, -2x, +4, +2i, and then +xi, and then -2i, and then -I squared. So what's nice about this is with the way I have it set up, I can start getting rid of some of these things like -xi and +xi. Those are gone. +2i and -2i. Those are gone. Also, don't forget, I squared goes to a -1. Since that goes to a -1, I'm taking the opposite of that one. This box will turn into a +1. So I can simplify a little bit here. So after I distribute the complex values, we're going to have, let's see here, x plus 1, x minus 2, and then I'm going to have x squared, -2x and -2x come together as a -4x, +4 and a +1 come together as a +5. Okay, so that's where I'm at after my first sets of distributions. Now I can keep going with this where I just take x minus 2, distribute it. I'm going to go ahead and just do x plus 1 and distribute with x minus 2. Okay, so if I do that, we'll have x times x is x squared, and then x times a -2 is a -2x. I can just do this as one step here. So I'm going to have -2x, +1x comes together as a -1x. And then 1 times a -2 is going to give me -2. Okay, So I'm almost ready to get my polynomial completely set up. My last step is to distribute this. I'm going to do one more 3x3 box. Okay. Since I have 3 terms times 3 terms, that's what's nice about this. If you use a box method like this, it's always going to be, your rows and columns will be the number of terms in each thing you're multiplying. So I've got 3 and 3, so I'm going to go with 3 rows and 3 columns. So I got x squared, negative 1x, minus 2, x squared, negative 4x, and a positive 5. So x squared times x squared is x to the 4th, negative 1x to the 3rd, negative 2x squared. Then x squared times negative 4x is a negative 4x to, x to the 3rd, positive 4x squared, then positive 8x. Down here, I'm going to have 5x squared, negative 5x, and then a negative 10. What's nice about this setup is that all of my like terms are organized very well. Like I can put my x cubes together here. I can do my x squareds are all right here. And I can get 8x and negative 5x there. It won't always line up on this diagonal like this, but it is still pretty easy to see where everything is. So my final step, my polynomial function that has all these zeros will be x to the 4th. Negative 4 minus 1 is a negative 5, x to the 3rd. Then 5 plus 4 is 9, minus 2 is a positive 7x squared. Negative 5 and a positive 8 is a positive 3x. And then minus 10. So this is my final answer here. Okay, so again, we can either solve for our zeros. We are going to use graphs, but along with our synthetic division and or more like we get it down to a quadratic, then you're just solving it out from there however you want. Or we take our given zeros and we can model our polynomials going backwards. Don't forget about the conjugate pairs. Anytime you have a complex zero, the conjugate pair is also going to be one of your zeros. All right, that's it for today. Take care, everyone.